it is my pleasure to introduce the principal engineer at Microsoft, Chinmay Nerurkar, my apologies. He will speak to us about building low-latency MI systems to supply real-time model predictions for online ad serving at scale. Please join me in welcoming to the stage Chinmay Nerurkar. Welcome.
Right. So, hey everyone, thank you for joining in. Someone mentioned I'm going to be talking about building low latency machine learning systems for online advertising at scale. So I'm Chinmay. I'm a principal engineer here at Microsoft Ads. And this presentation here builds on some of the lessons me and my dear colleague, Dr. Musa Taifi, we've learned while creating machine learning products over here. Unfortunately, he could not join us here today. So let's jump into it. Okay. So first, I'll go over like what AdTech is, how it works, and why is machine learning such a big deal when it comes to AdTech, right? Okay. So I work for a subdivision called Xandr, which is a part of Microsoft Advertising. And what Xandr does is it provides a premium advertising experience to internet users across digital, mobile, and CTV media or connected TV media globally. So let's unpack that a little bit, right? So on the buy side or the demand side, we have our advertiser clients who want to reach their target audience users and show their ads, sell their goods and services. On the other end, we have the sell side or the supply side, where we have publishers, which are websites or apps, mobile apps or streaming platforms that provide the real estate to show the ads to the viewers that they have, right? And central to all of this is the internet users who we want to connect with the goods and services that they would be most interested in while giving them a seamless, privacy compliant online viewing experience. So how does ad serving actually work? What does it mean for an ad to be served, right? So let's go over an example of this. Let's say you're a user who is visiting espn.com in your web browser, right? On the very right-hand side. So the web browser is going to send a message, an ad request to our ad server exchange saying, hey, there's a particular user trying to open up espn.com. Does anybody want to show them advertisements, right? Now the ad server exchange is going to go, if you look at the upper block, it's going to go enrich that ad request with contextual audience data, a few more advertisement context related markers, and then it's going to send the ad request to the bidding engines to solicit for ads, right? And the bidding engine is where the advertisers sit. Now, the job of the bidding engine is to go through all of the advertisers. Let's say you have tens of thousands of advertisers who might be interested in showing you an ad, and rank them using recommender systems to see which advertisements would be most suitable for you, the viewer, on espn.com. Then in final stage ads ranking, the few advertisers that are suitable to show you ads, we will try to find out how much should they bid in an online ads auction so that the winner gets to show you an ad, right? So here we further shortlist the number of ads that will be participating in the auction. And finally, when we figure out that there's like, hey, a few like 50 advertisers who should compete with each other for showing you the ad, then we actually go to ad creative selection. Ad creative is basically the image or the advertisement picture that you get shown or the video you see when you see the ad, right? So we select the right ad for the advertisers, and this information is sent back to the ad exchange. Here we run an ad auction. Whoever bids the highest wins and gets to show you the advertisement on espn.com. And of course, along the way, everything that happens, we capture all the information about the transaction in different kinds of data storage, data warehouses, et cetera, as shown at the bottom. So where does AI and machine learning come in all of this, right? So I've kind of shown the same diagram as before and highlighted where machine learning is involved in red. So as you can see, along every step of the way, you have some or the other machine learning process algorithm going on. When you're collecting, generating contextual audience data, we are using deep learning, graph neural network modeling to tie in contextual markers to enrich requests. In early stage ads ranking, we have deep learning embedding space similarity search algos. When we are calculating bid values, probabilities of events, clicks, conversions in final stage, we are using classical algos like logistic regression, deep learning models to compute dollar bid values. And creative selection, again, uses reinforcement learning to figure out like which is the best advertisement image to show you, right? And then there's more use cases. If you think about it, like we need to make sure there's no ad fraud happening. So we are trying our best to ensure that we are not showing you fraudulent advertisements that can steal your information. We are trying to make sure we are not showing advertisements on bad websites or clickbait websites so as to waste the advertiser's money. So there's a lot more applications behind the scenes where machine learning gets involved. Okay. So why is it such a big deal to do machine learning at scale in ad tech? So if you look at this one, our ad serving system is not like one application in one data center, right? We have over 1,000 application instances of our bidding engines and ad servers running globally in all continents, well, except Antarctica, right? Running closer to wherever the users are accessing their content, be it streaming media or websites or apps, right? Most ad auctions need to happen in a very short amount of time. Think about it. When you go to your web browser and click espn.com, you want it to open in a blink of an eye. If it takes like 4 or 5 seconds because we were trying to serve ads, you'll be turned away from the website. So they need to complete under 150 milliseconds. On a daily basis, we see about 600 billion ad requests globally, right? Of course, we filter out some of the bad requests and we conduct 400 billion auctions, which result in tens of billions of ad transactions. So serving a premium advertising experience globally, as I said, is a serious business. So now, why is machine learning latency an issue in all of this, right? So machine learning is very prevalent in every step of the way, as we saw above, right? And there have been a lot of studies by Google, by other large ad tech providers and independent firms, which show that users will get frustrated if we take too long to serve their content, which means like if they open an app and it takes like a good 4 or 5 seconds to open, they will get turned away from your application. You might lose them as a customer. They might go somewhere else, right? Advertisers will be unable to reach their target audience and sell their goods and services. So it's a loss of revenue, loss of hitting their goals for them. And publishers who are serving you content, they will lose a viewer. They'll lose their page views and ad revenue. So, right. So this is a lose-lose situation for pretty much everyone if machine learning latency is not addressed, right? So as important as machine learning is to ad tech and its success, it's important that machine learning does not become like the arch enemy of ad tech. So in this next section, I will go over some of the most common abstraction layers for where machine learning latency comes from. Again, this is based on like what we've observed and a few ideas to mitigate that. Okay. So number one, PSA of the day when it comes to machine learning latency, you want to focus on the machine learning serving latency first, because that is what your client is going to see first and judge your service for, right? So here we kind of put together a diagram showcasing how we sort machine learning latency seen in real-time larger systems, right? So we try to classify machine learning serving latency here, of course, as offline and online, right? So anything that is really, if your system can tolerate latency, reply latency of over 100 milliseconds, I'm going to call it offline, right? Because you have all the time you need to run your machine learning predictions, take your time to return the results to the user. You're not in a rush, right? But when you need to return your predictions fast within 100 milliseconds because your application demands it, your business demands it, then we get into the online machine learning serving world. I'm talking about serving latency. I'm not talking about training here. So just draw a distinction between online and offline processes, right? So some of the examples of online processes where online machine learning serving processes is like generating ad recommendations, or if you're basically opening your Netflix, then generating recommendations for what you want to view next. That needs to happen immediately. If you had to wait like 5 or 10 seconds for those results to come back, you'd be turned away from the service, right? Now, in online, again, we distinguish async predictions and synchronous predictions. So async is where you have some back and forth between processes before serving your machine learning prediction, right? So think of a user who's subscribed to a grocery subscription service, right? And this user starts tinkering around with their subscription settings in the browser. Now the browser sends a request back to the machine learning backend saying like, hey, we have the subscriber who's trying to tinker around with their subscription settings. What should we do? Should we send them an offer? Should we do something? And the backend says like, okay, like, no, let's wait. Let me get some more information. Let's see what they're trying to do, right? And then the user goes and tries to cancel their subscription, and the backend comes back saying like, hey, wait, if you don't cancel your subscription, I'll give you 3 months at a discounted rate, right? So that's async. That's like a back and forth process, right? On the other end, you have synchronous, where you're expected to reply right away. And that's where the pain kind of starts, right? At this point, like you're in a world where your synchronous online system is like some sort of a, let's say, a RESTful HTTP API or a gRPC API, whatever it be. The client is making a request for a machine learning prediction, and you have to reply with an answer right away. That's the expectation. Let's say like you have to get back to the client within 10 milliseconds with the prediction, with the answer, whatever, right? So that's where the real latency issues start. So I want to break down the cost of synchronous predictions into two separate parts, right? So we have machine learning prediction construction, and we have prediction serving. So you have a construction latency, which is basically the cost of actually evaluating the machine learning model. And then you have the serving latency, which comes to everything that you have to do from getting the client request to extracting features, to generating vectors or embeddings that can be fed to prediction construction. And then whatever prediction that you get, you have to like massage it back into a format, an answer that you can send it back to the client who asked for the prediction, right? So let's look into prediction construction itself, right? So there's a few things you can do if you want to optimize your prediction construction latency, right? You can optimize your models here by removing some of the supporting components. Let's say like while you're training your models, you're building your machine learning system, you add your debugging, logging, and those kind of code to your machine learning models. And some of that could be removed at this point if it's missing. So like you could remove some of the CRUD to make your models run faster. Maybe you could do something like run it on faster hardware, scale horizontally. So you can do things like these to actually speed up your machine learning construction. There are cases where we've seen gains by going in and parallelizing some of our custom machine learning algorithms to increase speed there, right? But at some point, like you also have to think of your model itself and see like, what you're trying to do with it to optimize. So we try to break it down into like two different kinds of like uh, optimization problem itself, where you're trying to solve for your optimizing metrics versus your satisficing metrics, right? So when you have a model, your optimizing metrics are things where you're trying to improve the model's predictive ability, right? So let's say you're trying to improve its like accuracy, precision, recall, all the good things that you do to evaluate your model and make it better. And every single thing you do there to improve those metrics is a win in an offline world. If you could take like 5 whole seconds to evaluate your model and give a result, you could give the best result you could. But on the other hand, you have to think of like what are your satisficing metrics when you're in the online world. When you need to get a reply back to your client within 10 milliseconds, you have to think about like, okay, where is my model being actually evaluated? Where is the prediction being constructed? Is it on a mobile device? Is it on a GPU farm somewhere? Will my model run fast enough wherever I'm deploying it, right? What is the network latency, right? Right? Can I get all the features in time to this particular model and run it, right? So you have to consider all of those things as your satisficing metrics, right? And you have to kind of solve for a balance between optimizing metrics and satisficing metrics to successfully deliver predictions within your latency budget. So common method to solve for these two metrics is the way we would do it is like, first of all, you want to set like your business acceptable satisficing metric threshold. So let's say business requirements say you need to serve your model within 10 milliseconds, right? So you start by setting that. Then you increase the complexity of the model little by little by adding features or by adding more layers to your deep neural network until like you hit your satisficing metrics threshold. At that point, you can check like, are you happy with the predictive accuracy of your model? Is it good enough, or do you still need something more? If you're happy with it, then you're ready to go to production. If not, then you have to start breaking down your model. You have to see what else you can do. Can you use a simpler model, like instead of a deep learning model, maybe use a regression model or something? Can you reduce the number of features inside your model? Can you reduce the number of hidden layers in your model? Like, what can you do to make your model evaluate faster, right? So that's how you would want to basically drive for this particular balance. Okay. So once you're done with that, you have to keep one thing in mind, like optimizing the model itself and the prediction construction latency itself is only going to take you so far, because distributed IO is going to be what's going to be taking away most of your latency, right? And where does this come from? So let's look into it. So the big things here is your prediction serving costs, right? So model construction is mostly computation. In model construction, you have a model, you have a feature vector or an embedding that is ready to be fed to the model, and all you have to do is score your input and get a prediction. Now you've done your job optimizing it, but we can't forget about the part where we are serving it, right? So when we get into serving, you're looking at, let's look at model inputs first, right? So when you're getting a request from the client, one thing to keep in mind is like that you're rarely ever getting all the features, or you're not getting a feature vector or an embedding on the client request. And most of the times you're not even getting like all the features that you need for scoring on your model, right? And features are basically the lifeblood of your model, and they're the drag in this whole operation, right? So when you're looking at features itself, there's three different kinds of features, right? So one is the user supplied features. And let's think in terms of, let's say, a streaming video service. As a user, you log in and the video service wants to show you recommendations of what you can watch, right? So when a request comes into the machine learning backend, user supplied feature would be the user identifier. Who is the user who's watching the video? Then there's other static reference features about the user. Let's say what kind of movies or shows has this user watched? What genres of media is this user interested in? So all of these things are actually stored based on based on the user's historical interactions with the service somewhere, right? And then there's dynamic real-time features, right? If a user is interested in a particular genre, what kind of ratings have other users recently given to, let's say, movies or shows in this genre? So these are dynamic real-time features which might be coming in while other users are interacting with the system, right? Now, with static reference features, one of the most common and easy use cases, like I need a single row with one column each for each of the features of customer X, right? That's how you're asking for features from the ML gateway. So think about it, like you get a user ID or you get a customer ID from your request, and you have to go and look up, okay, what genre of movies? That's like a single feature. Or like what is the previous 5 movies that this user has watched, like that's like 5 independent features. So you basically need this information about a customer that's probably stored somewhere in your data sets. So that's a simple way of thinking about it, right? The problem comes in when you have a lot of this data, and most of this data is actually stored in data warehouses, right, for large enterprises. And unfortunately, these data warehouses are not meant and they're not optimized to do real-time fast querying, right? So instead of data warehouses, they are basically optimized to store a lot of data, to run aggregations, joins, filtering, extensive star schema operations, right? So when a request comes in for predicting which movies to recommend to a user, you're not really realistically going to be able to go to a data warehouse and get a feature vector for this particular user in a short latency budget, convert it into an embedding or numerical vector, and feed it to the machine learning model. So one of the strategies is to periodically extract and aggregate these features, and you want to store these features in fast cache storage with some sort of a single key lookup. So next time a user ID comes in, you're able to look up like, this is what the features are from my user, and you're ready to feed those to the machine learning system. Right. We can't forget about the model outputs themselves, right? So we talked about prediction construction, optimizing the model itself, but you can't always evaluate your model, or it's expensive to evaluate your model sometimes in real time, every single time a request for a prediction comes in, right? So there's a couple of things you can do here, right? So a lot of times, if your model is not updated very frequently, some of the more complex models like deep learning models or embeddings-based models, they don't need to be updated extremely frequently, right? So you could pre-compute some of the results and store them for the next time they need to be looked up. Now, yeah, so if all of the techniques covered so far, they don't help you when reducing prediction latency, then you have to see how you can get model evaluation scoring out of the picture and pre-compute and cache predictions so that you can just look them up. Right. So that sounds easy, right? Like you basically pre-compute your predictions for all the users in the system and keep them ready at demand whenever they're needed next. But where's the problem here, right? So you could have entity-based lookup keys, let's say like your customer ID that comes in every single time, like someone logs into your streaming service or into your e-commerce platform, and you want to recommend them products to buy, right? So it could be entity-based, or you could use a combination of feature values, right? Show me, recommend me a song for someone who is in one of the countries, who is interested in one of the music genres, etc., etc. So it works well until you realize that basically having a lot of entities like increases cardinality, and that can be a latency killer, right? So think about it, like if you're running a technology forward trucking company, right? Where you're monitoring hundreds of your trucks on the road, like hundreds of parameters, trying to figure out like which one might break where. It's not that hard. It's not a high number. But if you're running like an e-commerce platform with like 100 million items in your product catalog, storing that efficiently and pre-computing predictions for all of those items, maybe for like hundreds of models, hundreds of different types of models, that's not going to be possible easily. You kind of run into a similar problem when you're talking about combination of feature values, right? So let's say, yeah, you want to figure out like, songs to serve to a user in a particular country, device type, song category. These are your features to the model, right? So as the number of these features increases significantly, uh, as you see, the cardinality is going to blow up a lot, right? So what can you do in this case, right? What you want to do is, in a lot of time, a lot of cases, like yes, you can pre-compute most of your or all of your predictions, and you could use some sort of a LRU cache, or least recently used, or like the most frequently seen keys can be stored in your fast cache, because that's what delivers the highest business value, and you should make sure they're facing the least latency at production time, right? And for the rest of the keys, you could have like a slightly slower cold cache where the predictions are cached, or you could run the prediction. You could basically actually predict the kind of the value of for particular low frequency keys at real time whenever needed, and you pay the cost of latency there. And of course, you have to think in terms of like, what is your optimizing versus satisficing metric threshold here. If you need all your keys for fast lookup, if all of them are important, then you need to go back to the business and change something. You either need like more expensive hardware, or you need a different model, or your business requirements need to give. Right. Now, there's another interesting application where you can cache and reuse predictions. And this is something that's becoming popular with the case of real-time similarity matching, especially with LLMs and embeddings-based world. Instead of, if you wanted to train a model where you're trying to find, especially like recommendations on products and things like that, right? So instead of doing exact searches on your vector databases, which are becoming more and more popular with LLMs getting more prevalent today, you could do something called an approximate nearest neighbor search, right? So you, instead of trying to find like all the exact matches, you're trying to find like most of the best matches and give that out as a result, right? So that is something that is becoming more and more popular with vector databases and LLMs becoming more common now. Okay. So what do you do like now if your cardinality is still high and your prediction latency is still high, right? So you can do things again, like, reduce the embedding size, like get a better, like try a different indexing scheme with your vector databases until like your prediction quality starts dropping. And if you still can't get like a proper satisfying trade-off between your optimizing and satisficing metrics, then you have to like look elsewhere. You need to go back to the business and try to refine your requirements. Okay. So some of the things that we've observed for low latency caching is like most of your databases and fast lookup databases, they're going to be optimized for single key lookups, not composite feature lookups. So you want to come up with some sort of a composite ID for your feature lookups, right? You want to keep an eye on how your cardinality is growing. You want to monitor it, because you could be caught off guard and it will blow up your database if you're not keeping track of what's happening as you add more and more features to your model, to your system, right? If you have continuous values in the system, that's going to blow up your database sizes, your lookup latency. So you ideally want to bucketize those things, right? So anything that basically helps you lower your cardinality for feature lookups and reverse lookups when you're serving answers for your predictions is going to help you a lot more than most of the other things. Okay. So now we can go over some of the actual AdTech latency cases that we see when we are trying to serve, when you're trying to find out ads to participate in an auction. So this is like the right hand side of the diagram that I shared above, and we look into the use case of the bidding engine receiving the ad request, the enriched ad request from the ad server, and it's expected to reply back with a fewer matching ads to participate in the ad auction and their bid values, right? So let's look at what happens at each stage of the way, right? So the first thing that we get into is early stage ads ranking, right? So here, the goal is to start with, say, a few tens of thousands of advertisers who want to show their ads to the user, right? And what we're trying to do is we are trying to use a deep learning neural network based or a graph neural network based recommendation model, where we're trying to shortlist it to, say, about like 200 or 300 or even fewer advertisements who will go further and participate in the rest of the auction process. So a naive approach to do this kind of a recommendation system would be when an ad request comes in, we want to extract the contextual features of the ad request. Then we construct a feature embedding, which is like a numerical vector based on the contextual features in real time. Then we run an exact search on the embeddings in our vector database to find all the matching ads that we might want to serve to this user. Then we go back to the database and look up the ads matching these selected embeddings, and then send these ads to the final stage ads ranking, right? Now, the pros of this approach is you have 100% recall. The cons is that everything else that we did is extremely expensive, right? Constructing contextual feature embeddings at runtime, it's a complex process. You have your models running, say, on a GPU machine, which is separate from where the vector database is stored potentially. So you're also incurring a lot of network latency here, hopping between a lot of processes. And exact search is expensive, right? So can we do better? Well, let's see. What if we use approximate nearest neighbor search, right? So ANN search is going to give us approximate results instead of exact results, as of course the name specifies. But you still get a very high recall if you use the right indexing scheme. Most modern vector databases will give you like 5 or 6 well-established, well-proven ANN algorithms like locality-sensitive hashing, HNSW, or Facebook has its own locality-sensitive hashing algorithm where you can basically run your predictions really fast with much low latency and pretty high recall, right? So now we've basically reduced the cost of model of prediction serving a little bit here, but we still have high construction cost here. So can we do even better? Absolutely. So as I mentioned, like some of these graph neural network models, they're not updated on a very high frequency. They might be updated like once every few days because ads and contextual features, the mapping between them doesn't change every minute or every few hours, right? So the models are not updated often enough. So we might be able to pre-compute and store which context map to which set of matching ads, right? And that's exactly what we do. So we pre-compute our embeddings for the contextual features that we most commonly see, and we pre-compute like which would be the best ads to show when we see that particular contextual embedding, right? So our system kind of looks like this now. So as you see, the bidding engine is talking directly to the contextual to ads lookup. It's a fast cache. You basically just give it a tuple or entity of contextual features, and you'll immediately get the pre-computed best ads to send to final stage ads ranking right away, right? And then there's other blocks where you will actually score the model and things like that if you need be. But the idea is to reduce the latency here by having the results ready. The next step is final stage ads ranking, where you basically take these 200 or 300 ads that you shortlisted, and now you want to screen them further. This is so final stage is more expensive uh, in certain ways than the early stage ads ranking, which is why we don't run this on all of the ads in the system, right? So in final stage ads ranking, one of the things among many other you're trying to do is a very common use case is computing the probability of a click and a conversion at times, right? So multiple models are evaluated to compute values, which eventually go into calculating the dollar bid value that's going to be bid into the ads auction, right? And some of the ads might not even make the cut, so we're going to reject it. Like we're going to say that these ads won't bid in the auction at all at this stage, right? So this particular model now is trained on historical data. It's trained a lot more often, every 2 to 3 hours, as transactions, as ads requests comes in for this particular ad campaign, right? So these models are updated more frequently. There's about 15 to 20 different features from an ad request that goes in as an input into the model, right? So here, you would not be able to pre-compute and cache the results a lot of times because we have a very high cardinality of input features, right? Uh, Countries, like what kind of device ID, what kind of browser, like a bunch more. So the cardinality really blows up to a point where you cannot really have a database where you can pre-compute and look up. Also, your models are updating often. So you can just like keep on pre-computing results again and again and again and again if you want to keep your predictions fresh, right? Now you can, let's say, implement this as a typical machine learning service API, as I mentioned, or like a REST or a HTTP API that the bidding engine can continue talking to, right? But at this point, so the LR model or a deep learning evaluation model, the cost of evaluating, scoring that model, so prediction construction cost is much lower than model serving cost, mainly because of network latency. So the optimal design choice here for us was to actually move the model scoring inside the bidding engine, right? So as you can see here, what we do is the model evaluation, the model scoring happens actually inside the same process application instance as inside the bidding engine. And models are trained and fed, updated, cached inside the bidding engine for evaluation as ad request comes in, right? So that gives us the highest performance, the least latency to evaluate these models fast and shortlist them even further for the next stage. Now, let's say out of the 200 or 300, you shortlisted like about 50 advertisements that, along with their dollar bid values, that will participate in the auction. So the next thing you want to do is you want to find the right creative to show to the user. Right. So the goal here is to find the best creative for the ad request, right? And creatives are something that advertisers will keep on updating, playing around with, even for the same product, a lot more often and unpredictably, right? They will also have different creatives for the same product in different geos, in different states, in different languages, depending on where they're trying to sell the same product, right? So if Nike is selling shoes in the Americas and in Asia, they might be selling the same product, but it'll be in different languages, it'll have different images, things like that, right, for the same product. So that's where we have to continuously take into account like the feedback of how that particular creative is performing and use that feedback to train our reinforcement learning models. So again, because the model is being updated continuously, you can pre-compute and cache these, right? And ad creatives, as I said, like advertisers like to change, tinker with this data, very unpredictability, much more often than most of the things in the system, right? Moving add creative selection into the bidding engines like we did with final stage ads ranking is not optimal because ad creatives and metadata can consume a lot of memory, and evaluating and updating these RL models in real time, which happens a lot, is going to take a lot of time, a CPU from rest of the stuff that happens in bidding engines, again adding to your latency in that way, right? So an optimal solution here that worked for us was to have a model serving API, a separate process where you can score, evaluate these ad creative models in real time, update these models in real time, scale them horizontally as we require, depending on where, what geos we are operating in based on the demand uh, at the time of day, right? So the right solution for us to build ad creative selection as a machine learning as a service outside the bidder that the bidding engine can talk to over HTTP or gRPC. So this is how like our system looks like. And at the end, now that you've figured out like the 50 ads that want to bid into the auction with their bid values and the creatives they want to show, you send those matching ads back to the ad server, an auction is run, and the winning ad and the creative gets displayed to the user in their app, browser, streaming service, whatever it is. Right. So some of the things that we have learned along the way, building all these different kind of things in real-time system that operates at a global scale, right? So number one thing when you're building a ML dependent system is like you want to focus on your ML serving latency at the very first, right? Because that's where you're going to get most of your latency from. That's what the client sees first. If you do it wrong, you're going to lose business, right? Optimizing your model itself will only take you so far. You always have to keep an eye on your input, real-time model input construction and distributed IO. One of the tips like I would give is always include your model into your hot path at the beginning of development. Because what might happen is like you might build this like model that works really well in the offline world. It satisfies all of your optimizing metrics. The prediction errors are amazing. And then you plug it into your process and you realize that you're not able to serve it fast enough. You're timing out, right? And then you have to go back to the drawing board. So you want to start your model development with the development of the rest of the application, plug it in right away in the hot path. This way, you're not falling back on it. And one more thing that most people discount is pre-calculating and caching predictions using things like approximate searches, similarity searches, and things like that. A lot of data scientists and engineers want to update their models often and serve their predictions in real time. Think about like if that's really required. Like, does it make a difference? Does your model update often enough? Do your predictions change often enough? Do you need to evaluate your model in real time? If the answer is no, you can get humongous gains by pre-computing your predictions and caching them and just making it a lookup, right? Yep. So these are some of the lessons that I wanted to share, and that's it. Thank you, guys. I'll open it up to questions if anyone has them.
Testing. Thank you very much, Chinmay. Forgive me, is it Chinmay or Chinmay? If you could correct me.
It's the first one, Chinmay.
Chinmay, okay. Thank you so much for sharing such a thorough explanation of all of your work. We will take a few moments now for a question and answer period. Ladies and gentlemen, please, as usual, you can use the QR code to submit any questions. Just going to give you 1 minute, and then we will get into the Q&A.
Do I need to turn it on manually?
All right, first question. How can the issue of latency be addressed when the program interacts with an external API and caching is not always a feasible solution?
Okay, and
Repeat the question.
Yeah, I'll repeat. How can the issue of latency be addressed when the program interacts with an external API and caching is not always a feasible solution?
Well, when the program
You missed the question again? My apologies.
oh no, I'm just echoing. So if you're seeing high latency and you're interacting with an external API, like you cannot use caching, right? Like then at that point you have to some of the things you might have to do is move your machine learning machine learning solutioning or scoring mechanism or wherever your machine learning layer is closer to where you need the predictions, right? So this is a common problem. If you have your machine learning serving in a different data center than where you're serving your predictions to an application, you cannot fight network latency. We've had this issue, especially with the global system, where we have our ad serving engines and we have our like bidding engines and like one DC in Europe, and we are trying to serve our predictions from New York. There's not much you can do to fight this network latency. It just comes down to like how the networks work. So you have two options. Like you either go back to your business and see if you can tolerate that latency, if you can reduce your, you said caching is not possible, right? So the main thing that you have at your disposal is to move your model scoring closer to where you need it. Unfortunately, you cannot fight network latency.
Thank you so much for the answer. And one last question before we wrap up. Do you imagine recognition on the ad images to identify relevancy during the ad matching?
Okay. If I understand the question correctly, so you're asking if I could do image processing on the ad images or ad creatives in early stage ads ranking. So that is something that we have considered, but we found that to be inefficient, mainly because advertisers keep on changing their creatives, keep on like updating the creatives a lot more often than we can include that as a signal in our early stage ad ranking for recommendation. So we tried that, but that doesn't work, which is why we created creative selection as a separate ML process itself.
Thank you
So to
very
answer your
much.
question, technically, yes, like it would be a good signal into early stage ads ranking, but it's not possible to train your models and keep them updated fast enough with it.
Thank you so much. There are many, many more questions coming in, but unfortunately, in the interest of time, we'll wrap up the Q&A here. But please feel free to connect on LinkedIn for any follow-up questions that you have. All of our speakers are constantly available for your questions. Thank you so much. Join me in thanking Chinmay for being with us today, and thank you for sharing your expertise.
Thank you for having me here. Thanks, everyone.